I talked to a guy named Charles Hoskinson. He mentioned that he's collaborating with you. He's an interesting guy. He sends me papers on speaking of automated theorem proving a lot. He's exceptionally well read on that area as well. So what's the nature of your collaboration with him? He's the creator of Cardano. What's the nature of the collaboration between Cardano and the whole space of blockchain and Wolfram, Wolfram Alpha, Wolfram blockchain, all that kind of stuff?
Well, okay, we're segueing to a slightly different world, so although not completely unconnected,
right? The whole thing is somehow connected.
I know. I mean, the strange thing in my life is I've sort of alternated between doing basic science and doing technology about 5 times in my life so far. And the thing that's just crazy about it is, every time I do one of these alternations, I think there's not going to be a way back to the other thing. And like I thought for this physics project, I thought, we're doing fundamental theory of physics. Maybe it'll have an application in 200 years. But now I've realized, actually, this multi-computation idea is applicable here and now. And in fact, it's also giving us this way. I'll just mention one other thing, and then we're going to talk about blockchain. The question of actually that relates to several different things, but one of the things about okay, so our Wolfram language, which is our attempt to kind of represent everything in the world computationally. And it's the thing I kind of started building 40 years ago in the form of actual Wolfram language 35 years ago. It's kind of this idea of can we express things about the world in computational terms? And, we've come a long way in being able to do that. Wolfram Alpha is kind of the consumer version of that, where you're just using natural language as input, and it turns it into our symbolic language. And that's, the symbolic language, Wolfram language, is what people use and have been using for the last 33 years. Actually, Mathematica, which is its first instantiation, will be 1/3 of a century old in October.
Wow.
It's kind of interesting.
What do you mean 1/3 of a century? Does that mean 33 or 30? What are we?
33 and a third.
33 and a third.
But
I've never heard of anyone celebrating that anniversary, but I like it.
I know, 1/3 of a century though. It's like you don't get many slices of a century that are interesting.
Yeah.
But I think that the thing that's really striking about that is that means including the whole sort of technology stack I built around that's about 40 years old, and that means it's a significant fraction of the total age of the computer industry. And I think it's cool that we can still run, Mathematica version 1 programs today and so on, and we've sort of maintained compatibility, and we've been just building this big tower all those years of just more and more and more computational capabilities. It's sort of interesting. We just made this picture of kind of the different kind of threads of computational content, of mathematical content and all sorts of things with data and graphs and whatever else. And what you see in this picture is about the first 10 years. It's kind of like it's just a few threads, and then about maybe 15, 20 years ago, it kind of explodes in this whole collection of different threads of all these different capabilities that are now part of Wolfram language and representing different things in the world. But the thing that was super lucky in some sense is it's all based on one idea. It's all based on the idea of symbolic expressions and transformation rules for symbolic expressions, which was kind of what I originally put into this SMP system back in 1979 that was a predecessor of the whole Wolfram language stack. So that idea was an idea that I got from sort of trying to understand mathematical logic and so on. It was my attempt to kind of make a general human comprehensible model of computation, of just everything is a symbolic expression and all you do is transform symbolic expressions. And, in retrospect, I was very lucky that I understood as little as I understood then, because had I understood more, I would have been completely freaked out about all the different ways that kind of model can fail. Because what do you do when you have a symbolic expression, you make transformations for symbolic expressions? Well, for example, one question is there may be many transformations that could be made in a very multi-computational kind of way. But what we're doing is we're using the first transformation that applies. And we keep doing that until we reach a fixed point. And that's the result. And that's kind of it's kind of a way of sort of sliding around the edge of multi-computation. And back when I was working on SMP and things, I actually thought about these questions about how, what determines this kind of evaluation path. So, for example, you work out Fibonacci. Fibonacci is a recursive thing. F of n is f of n minus 1 plus f of n minus 2. And you get this whole tree of recursion, right? And there's the question of how do you evaluate that tree of recursion? Do you do it sort of depth first, where you go all the way down one side? Do you do it breadth first, where you're kind of collecting the terms together, where you know that, f of 8 plus f of 7, f of 7 plus f of 6, you can collect the f of 7s and so on. These are, I didn't realize it at the time. It's kind of funny. I was working on gauge field theories back in 1979, and I was also working on the evaluation model in SMP, and they're the same problem. But it took me 40 more years to realize that. And this question about how you do this sort of evaluation front, that's a question of reference frames. It's a question of kind of the story of that is basically this question of in what order is the universe evaluated. And so what you realize is there's this whole sort of world of different kinds of computation that you can do sort of multi-computationally, and that's an interesting thing. It has a lot of implications for distributed computing and so on. It also has a potential implication for blockchain, which we haven't fully worked out, which is, and this is not what we're doing with Cardano, but this is a different thing. This is something where one of the questions is when you have, in a sense, blockchain is a deeply sequentialized story of time, because in blockchain there's just one copy of the ledger, and you're saying this is what happened. Time has progressed in this way, and there are little things around the edge as you try and reach consensus and so on. And actually, we just recently we'd had this little conference we organized about the theory of distributed consensus, because I realized that there are a bunch of interesting things that some of our science can tell one about that. But that's a different. Let's not go down that path.
Yeah. But distributed consensus, that still has a sequential. There's like
there's
one
still
ledger.
Sequentiality. So
you don't tell me you're thinking through like how to apply multi-computation to blockchain.
Yes. And so that becomes a story of, instead of transactions all having to settle in one ledger, it's like a story of all these different ledgers, and they all have to have some ultimate consistency, which is what causal invariance would give one. But it can take a while. And the it can take a while is kind of like quantum mechanics. So it's kind of what's happening is there are these different paths of history that correspond to, in one path of history, you got paid this amount. In another path of history, you got paid this amount. In the end, the universe will always become consistent. Now the way it works is, okay, it's a little bit more complicated than that. What happens is the way space is knitted together in our theory of physics is through all these events. And the idea is that the way that economic space is knitted together is there are these autonomous events that essentially knit together economic space. So there are all these threads of transactions that are happening, and the question is, can they be made consistent? Is there something forcing them to be sort of a consistent fabric of economic reality? And sort of what this has led me to is trying to realize, how does economics fundamentally work? And what is economics? And what are the atoms of economics, right, so to speak? And so what I've kind of realized is that sort of perhaps, I don't even know if this is right yet, there's sort of events in economics that are transactions. There are states of agents that are kind of the atoms of economics. And then transactions are kind of agents transact in some way, and that's an event. And then the question is, how do you knit together sort of economic space from that? What is there in economic space? Well, all these transactions, there's a whole complicated collection of possible transactions. But one thing that's true about economics is we tend to have the notion of a definite value for things. We could imagine that, you buy a cookie from somebody and they want to get a movie ticket, and there is some way that AI bots could make some path from the cookie to the movie ticket by all these different intermediate transactions. But in fact, we have an approximation to that, which is we say they each have $1 value, and we have this kind of numeraire concept of there's just a way of kind of taking this whole complicated space of transactions and parsing it in something which is a kind of a simplified thing that is kind of like our parsing of physical space. And so my guess is that yet again, I mean, it's crazy that all these things are so connected. This is another multi-computation story, another story of where what's happening is that the economic consciousness, the economic observer, is not going to deal with all of those different microscopic transactions. They're just going to parse the whole thing by saying, there's this value, it's a number. Mm-hmm. And that's their understanding of their summary of this economic network. And there will be all kinds of things, like there are all kinds of arbitrage opportunities, which are kind of like the quantum effects in this whole thing. And that's, and places where there's sort of different paths that can be followed and so on. And so the question is, can one make a sort of global theory of economics? And then my test case is, again, what is time dilation in economics? And I know if you imagine a very agricultural economics where people are growing lettuces in fields and things like this, and you ask questions about, well, if you're transporting lettuces to different places, what is the value of the lettuces after you have to transport them versus if you're just sitting in one place and selling them? And you can kind of get a little bit of an analogy there. But I think there's a better and more complete analogy. And that's the question of, is there a theory like general relativity that is a global theory of economics? And is it about something we care about? Mm-hmm. It could be that there is a global theory, but it's about a feature of economic reality that isn't important to us. Now, another part of the story is, can one use those ideas to make essentially a distributed blockchain, a distributed generalization of blockchain, kind of the quantum analog of money, so to speak, where you have, for example, you can have uncertainty relations where you're saying, well, if I insist on knowing my bank account right now, there'll be some uncertainty. If I'm prepared to wait a while, then it'll be much more certain. And so there's, is there a way of using, and so we've made a bunch of prototypes of this, which I'm not yet happy with, because what I realized is, to really understand these prototypes, I actually have to have a foundational theory of economics. And so that's kind of it may be that we could deploy one of these prototypes as a practical system, but I think it's really going to be much better if we actually have an understanding of how this plugs into kind of the economic system.
And that means like a fundamental theory of transactions between entities.
Well,
that's what you mean by economics.
Yes, I think so. But I mean, how there emerge sort of laws of economics. I don't even know, and I've been asking friends of mine who are economists and things, what is economics? Is it an axiomatic theory? Is it a theory that is a kind of a qualitative description theory? Is it, what kind of a theory is it? Is it a theory, what kind of thinking? It's like in biology, in evolutionary biology, for example, there's a certain pattern of thinking that goes on in evolutionary biology where if you're a good evolutionary biologist, somebody says that creature has a weird horn. Mm-hmm. And they'll say, well, that's because this and this and this, and there's selection of this kind, and that's the story. And it's not a mathematical story. It's a story of a different type of thinking about these things. By the way, evolutionary biology is yet another place where it looks like this multi-computational idea can be applied. And that's where maybe speciation is related to things like event horizons, and there's a whole other kind of world of that. But
it seems like this kind of model can be applicable in so many aspects, like at the different levels of understanding of our reality. So it could be at the biology, at the chemistry, at the physics level, right, the economics, and you could potentially. So the thing is, it's like, okay, sure, at all these levels it might rhyme, it might make sense as a model. The question is, can you make useful predictions at one of these levels?
And that's right, and that's really a question of, it's a weird situation because it's a situation where the model probably has definite consequences. The question is, are they consequences we care about?
Yeah,
and that's some, and so in the case of, in the economic case, the the one thing is this idea of using kind of physics-like notions to construct a kind of distributed analog of blockchain. Okay, the much more pragmatic thing is a different direction, and it has to do with this computational language that we built to describe the world that knows about, different kinds of cookies and knows about different cities and knows about how to compute all these kinds of things. One of the things that is of interest is if you want to run the world, you need, with contracts and laws and rules and so on, there are rules at a human level, and there are kind of things like And so this gets one into the idea of computational contracts. Right now, when we write a contract, it's a piece of legalese. It's just written in English, and it's not something that's automatically analyzable, executable, whatever else. It's just English. Back in Gottfried Leibniz, back in 1680 or whatever, was like going to figure out how to use logic to decide legal cases and so on. And he had kind of this idea of, let's make a computational language for the human law. Forget about modeling nature, forget about natural laws. What about human law? Can we make kind of a computational representation of that? Well, I think finally we're close to being able to do that. And one of the projects that I hope to get to, as soon as there's a little bit of slowing down of some of this Cambrian explosion that's happening, is a project I've been meaning to really do for a long time, which is what I'm calling a symbolic discourse language. It's just finishing the job of being able to represent everything, like the conversation we're having, in computational terms. And one of the use cases for that is computational contracts. Another use case is something like the constitution that says what we want the AIs to do.
So, but this is useful. So you're saying, so these are like, you're saying computational contracts, but smart contracts. This is what's in the domain of cryptocurrencies known as smart contracts. And so the language you've developed, this symbolic, or seek to further develop symbolic discourse language, enables you to
write a contract.
Write a contract that richly represents
the world.
Some aspect of the world. Yeah.
But I mean, smart contracts tend to be right now mostly about things happening on the blockchain.
Yes.
And sometimes they have oracles. And in fact, our Wolfram Alpha API is the main thing people use to get information about the real world, so to speak, within smart contracts.
So Wolfram Alpha, as it stands, is a really good oracle for whoever wants to use it. That's perhaps where the relationship with Cardano is.
Yeah, well, that's how we started getting involved with blockchains, is we realized people were using, Wolfram Alpha as the oracle for smart contracts, so to speak. And so that got us interested in blockchains in general. And what was ended up happening is Wolfram language is, with its symbolic representation of things, is really very good at representing things like blockchains. And so I think we now have, we don't really know all the comparisons, but we now have a really nice environment within Wolfram language for dealing with the sort of, for representing what happens in blockchains, for analyzing what happens in blockchains. We have a whole effort in blockchain analytics. We've sort of published some samples of how that works. But it's, because our technology stack, Wolfram language and Mathematica, are very widely used in the quant finance world, there's a sort of immediate co-evolution there of sort of the quant finance kind of thing and blockchain analytics. And that's so it's kind of the representation of blockchain in computational language. Then ultimately, it's kind of like, how do you run the world with code? That is, how do you write sort of all these things which are right now regulations and laws and contracts and things in computational language. And kind of the ultimate vision is that sort of something happens in the world, and then there's this giant domino effect of all these computational contracts that trigger based on the thing that happened. And there's a whole story to that. And of course, I like to always pay attention to the latest things that are going on. And I kind of like blockchain because it's another rethinking of kind of computation. It's kind of like, cloud computing was a little bit of that, of sort of persistent kind of computational resources and so on. And, this multi-computation is a big rethinking of kind of what it means to compute. Blockchain is another bit of rethinking of what it means to compute. The idea that you lodge kind of these autonomous lumps of computation out there in the blockchain world. And one of the things that just sort of for fun, so to speak, is we've been doing a bit of stuff with NFTs, and we just did some NFTs on Cardano, and we'll be doing some more. And we did some cellular automaton NFTs on Cardano, which people seem to like quite a bit. One of the things I've realized about NFTs is that there's kind of this notion, and we're really working on this. I like recording stuff. One of the things that's come out of kind of my science, I suppose, is this history matters type story of, it's not just the current state, it's the history that matters. And I don't think this is, actually realizing maybe it's not coincidental that I'm sort of the human who's recorded more about themselves than anybody else. And then I end up with these science results that say history matters, which was not those things. I didn't think those were connected, but
they're at least correlated, yes.
Yeah, right. So, this question about sort of recording what has happened and having sort of a permanent record of things. One of the things that's kind of interesting there is, you put up a website and it's got a bunch of stuff on it, but, you have to keep paying the hosting fees or the thing's going to go away. Mm-hmm. But one of the things about blockchains kind of interesting is if you put something on a blockchain and you pay, your commission to get that thing, put on, put on the blockchain, then in a sense, everybody who comes after you is, they are motivated to keep your thing alive because that's what keeps the consistency of the blockchain. So in a sense, with sort of the NFT world, it's kind of like if you want to have something permanent, well, at least for the life of the blockchain, but even if the blockchain goes out of circulation, so to speak, there's going to be enough value in that whole collection of transactions that people are going to archive the thing. But that means that, pay once and you're lodged in the blockchain forever. And so we've been kind of playing around with sort of a hobby thing of mine of thinking about sort of the NFTs and how you and sort of the consumer idea of kind of it's the opposite of the Snapchat view of the world.
That's right.
So
there's a permanence to it that's heavily incentivized, and thereby you can have a permanence of history.
Right, and that's kind of the now. So that's one of the things we've been doing with Cardano, and it's kind of fun. I think that this whole question about, you mentioned automated theorem proving and blockchains and so on. And as I've thought about this kind of physics-inspired distributed blockchain, obviously the sort of the proof that it works, that there are no double spends, there's no whatever else, that proof becomes a very formal kind of almost a matter of physics, so to speak. It's been an interesting thing for the practical blockchains to do kind of actual automated theorem proving, and I don't think anybody's really managed it in an interesting case yet. It's a thing that people aspire to, but I think it's a challenging thing because basically the point is one of the things about proving correctness of something is, people say I've got this program and I'm going to prove it's correct. And it's like, what does that mean? You have to say what correct means. I mean, it's kind of like, then you have to have another language. And people were very confused back in past decades of, we're going to prove the correctness by representing the program in another language, which we also don't know whether it's correct. And, often by correctness, we just mean it can't crash or it can't scribble on memory. But the thing is that there's this complicated trade-off because as soon as you're really using computation, you have computational irreducibility, you have undecidability. If you want to use computation seriously, you have to kind of let go of the idea that you're going to be able to box it in and say, we're going to have just this happen and not anything else. I mean, this is an old fact. I mean, Gödel's theorem tries to say, Peano arithmetic, the axioms of arithmetic, can you box in the integers and say these axioms give just the integers and nothing but the integers? Gödel's theorem showed that wasn't the case. There's you can have all these wild, weird things that obey the Peano axioms but aren't integers. And there's this kind of infinite hierarchy of additional axioms you would have to add. And it's kind of the same thing. You don't get to, if you want to say, I want to know what happens, you're boxing yourself in, and there's a limit to what can happen, so to speak. So it's a complicated trade-off, and it's a big trade-off for AI, so to speak. It's kind of like, do you want to let computation actually do what it can do, or do you want to say, no, it's very, very boxed in to the point where we can understand every step? And that's kind of a thing that becomes difficult to do. But that's in general, I would say one of the things that's kind of complicated in my sort of life and the whole sort of story of computational language and all this technology and science and so on. I mean, I kind of, in the flow of one's life, it's sort of interesting to see how these things play out because I've kind of concluded that I'm in the business of making kind of artifacts from the future, which means, there are things that I've done. I don't know, this physics project, I don't know whether anybody would have gotten to it for 50 years. The fact that Mathematica is a third of a century old, and I know that a bunch of the core ideas are not well absorbed. I mean, that is, people finally got this idea that I thought was a triviality of notebooks. That was 25 years. And, some of these core ideas about symbolic computation and so on are not absorbed. I mean, people use them every day in Wolfram language and, do all kinds of cool things with them. But if you say, what is the fundamental intellectual point here? It's not well absorbed. And it's something where you kind of realize that you're sort of building things. And I kind of made this thing about, we're building artifacts from the future, so to speak. And I mentioned that it's we have a conference it's coming up actually in a couple of weeks, our annual technology conference, where we talk about all the things we're doing. So I was talking about it last year about, we're making artifacts from the future. And I was kind of like, I had some version of that was kind of a dark and frustrated thing of like, I'm building things which nobody's going to care about until long after I'm dead, so to speak. But then I realized, people were sort of telling me afterwards, that's exactly how, we're using Wolfram language in some particular setting in, some computational X field or some organization or whatever. And it's like people are saying, oh, what did you manage to do? Well, we know that in principle it will be possible to do that, but we didn't know that was possible now. And it's kind of like that's sort of the business we're in. And in a sense, with some of these ideas in science, I feel a little bit the same way, that there are some of these things where, some things like, for example, this whole idea. Well, so to relate to another sort of piece of history and the future. One of, we mentioned at the beginning kind of complexity as this thing that I was interested in back 40 years ago and so on. Where does complexity come from? Well, I think we kind of nailed that. The answer is, in the computational universe, even simple programs make it. And that's kind of the secret that nature has that allows you to make it. So that's kind of the, that's that part. But the bigger picture there was this idea of this kind of computational paradigm, the idea that you could go beyond mathematical equations, which have been sort of the primary modeling medium for 300 years. And so it was like, look, it is inexorably the case that people will use programs rather than just equations. And, I was saying that in the 1980s, and people were, I published my big book, New Kind of Science, that'll be 20 years ago next year, so in 2002. And people are saying, oh, no, this can't possibly be true. We know for 300 years we've been doing all this stuff, right? To be fair, I now realize on a little bit more analysis of what people actually said, in pretty much every field other than physics, people said, oh, these are new models. That's pretty interesting. In physics, people were like, we've got our physics models. We're very happy with them.
Yeah, in physics, there's more resistance because of the attachment and the power of the equations. Right. The idea that programs might be the right way to approach this field there's some resistance. And like you're saying, it takes time. For somebody who likes the idea of time dilation and all these applications, I thought you would understand this.
Yeah, right. But and computational irreducibility.
Yes, exactly.
But I mean, it is really interesting that just 20 years, a span of 20 years, it's gone from, pitchforks and horror to, we get it. And, it's helped that we've, in our current effort in fundamental physics, we've gotten a lot further, and we've managed to put a lot of puzzle pieces together that make sense. But the thing that I've been thinking about recently is this field of complexity. So I've kind of was a sort of a field builder. Back in the 1980s, I was kind of like, okay, can we, I'd understood this point that there was this sort of fundamental phenomenon of complexity, and it showed up in lots of places. And I was like, this is an interesting sort of field of science. And I was recently was reminded, I was at the very first sort of get together of what became the Santa Fe Institute. And I was like, in fact, there's even an audio recording of me sort of saying, people have been talking about, what should this outfit do? And I was saying, well, there is this thing that I've been thinking about. It's this kind of idea of complexity.
Nice.
And it's kind of like, and that's what that ended up.
And
kind
you
of
planted the seed of complexity at Santa Fe. That's beautiful. That's a beautiful vision.
But I mean, but what's happened then is this idea of complexity, and and I started the first research center at University of Illinois for doing that, in the first journal, Complex Systems, and so on. And it's kind of an interesting thing in my life, at least, that it's kind of like you plant this seed, you have this idea, it's a kind of a science idea, you have this idea of sort of focusing on the phenomenon of complexity. The deeper idea was this computational paradigm, but the nominal idea is this kind of idea of complexity. Okay, then you roll time forward 30 years or whatever, 35 years, whatever it is, and you say, what happened? Okay, well, now there are 1,000 complexity institutes around the world, I think, more or less. We've been trying to count them. And there are 40 complexity journals, I think. And so it's kind of like, what actually happened in this field, right? And I look at a lot of what happened, and I'm like, I have to admit to some eye rolling, so to speak, because it's kind of like what's actually going on? Well, what people definitely got was this idea of computational models. And then but they thought one of the kind of cognitive mistakes, I think, is they say we've got a computational model, and and we're looking at a system that's complex, and our computational model gives complexity. By golly, that must mean it's right. And unfortunately, because complexity is a generic phenomenon and computational irreducibility is a generic phenomenon that actually tells you nothing. And so then the question is, well, what can you do? There's a lot of things that have been sort of done under this banner of complexity. And I think it's been very successful in providing sort of an interdisciplinary way of connecting different fields together.
Which is powerful in itself.
Right. I mean, that's a very useful
and economics. And it is.
Right. It's physics. A good organizing principle. But in the end, a lot of that is around this kind of computational paradigm, computational modeling. That's the raw material that powers that kind of correspondence, I think. And the question is sort of what is I was just thinking recently, we've been for years, people have told me, you should start some Wolfram Institute that does basic science. All I have is a company that builds software, and we have a little piece that does basic science as kind of a hobby. People are saying, you should start this Wolfram Institute thing. And I've been, because I've known about lots of institutes, and I've seen kind of their flow of money and kind of, what happens in different situations and so on. So I've been kind of reluctant, but I have realized that, what we've done with our company over the last 35 years, we built a very good machine for doing R&D and, innovating and creating things. And I just applied that machine to the physics project. That's how we did the physics project in a fairly short amount of time with a efficient machine with, various people involved and so on. And so, it works for basic science. And it's like, we can do more of this. And so
in
now,
biology and chemistry, so it's become an institute.
Yes, well, it needs to become an institute,
an official institute,
right? But the thing that I was thinking about. Okay, so what do we do with complexity? What there are all these people who've what should happen to that field?
Yeah.
And what I realized is there's kind of this area of foundations of complexity that's about these questions about simple programs, what they do, that's far away from a bunch of the detailed applications that people. Well, it's not far away. It's the under the bedrock underneath those applications. And so I realized recently, this is a recent kind of little innovation of a sort, a post that I'll do very soon. About kind of the foundations of complexity. What really are they? I think they're really two conceptual ideas that I hadn't really enunciated, I think, before. One is what I call meta-modeling. The other is ruleology. So what is meta-modeling? So meta-modeling is you've got this complicated model, and it's a model of, hedgehogs interacting with this, interacting with that. And the question is, what's really underneath that? What is it? Is it a Turing machine? Is it a cellular automaton? What is the underlying stuff underneath that model? And so there's this kind of meta-science question of, given these models, what is the core model? And I realized, to me, that's sort of an obvious question, but then I realized I've been doing language design for 40 years, and language design is exactly that question. Underneath all of this detailed stuff people do, what are the underlying primitives? And that's a question people haven't tended to ask about models. They say, well, we've got this nice model for this and that and the other. What's really underneath it? And what, because once you have the thing that's underneath it, well, for example, this multi-computation idea is an ultimate meta-modeling idea, because it's saying underneath all these fields is one kind of paradigmatic structure. Yeah. And, you can imagine the same kind of thing at much more sort of much sort of shallower levels in different kinds of modeling. So there's the first activity is this kind of meta modeling, the kind of the models about models, so to speak. What's drilling down into models. That's one thing. The other thing is this thing that I think we're going to call ruleology, which is kind of okay, you've got these simple rules. You've got cellular automata, you've got Turing machines, you've got substitution systems, you've got register machines, you've got all these different things. What do they actually do in the wild? And this is an area that I've spent a lot of time, working on. It's a lot of stuff in my new kind of science book is about this. This new book I wrote about combinators is full of stuff like this. And this journal, Complex Systems, has lots of papers about these kinds of things. But there isn't really a home for people who do rheology, or what I'm now,
as you call, the basic science of rules.
Yes, right. So it's like you've got some. What is it? Is it mathematics? No, it isn't really like mathematics. In fact, from my now understanding of metamathematics, I understand that it's the molecular dynamics level. Mm-hmm. It's not the level that mathematicians have traditionally cared about. It's not computer science, because computer science is about writing programs that do things, that were for a purpose, not programs in the wild, so to speak. It's not physics. It doesn't have anything to do with, it may be underneath some physics, but it's not physics as such. So it just hasn't had a home. And if you look at, but what's great about it is it's a surviving field, so to speak. It's something where, one of the things I find sort of inspiring about mathematics, for example, is you look at mathematics that was done, in ancient Greece, ancient, Babylon, Egypt, and so on. It's still here today. Mm-hmm. You find an icosahedron that somebody made in ancient Egypt. You look at it, oh, that's a very modern thing. It's an icosahedron. Mm-hmm. It's a timeless kind of activity. And this idea of studying simple rules and what they do, it's a timeless activity. And I can see that over the last 40 years or so as, even with cellular automata, it's kind of like, you can sort of catalog what are the different cellular automata used for. And, like the simplest rules, like one, you might even know this one, Rule 184. It's Rule 184 is a minimal model for road traffic flow. Mm-hmm. And, it's also a minimal model for various other things. But it's kind of fun that you can literally say, Rule 90 is a minimal model for this and this and this. Rule 4 is a minimal model for this. And it's kind of remarkable that you can just in this raw level of this kind of study of rules, they then branch, they're the raw material that you can use to make models of different things. So it's a very pure basic science, but it's one that, people have explored it, but they've been kind of a little bit in the wilderness. And I think, one of the things that I would like to do finally is I always thought that sort of this notion of pure NKS, and NKS being the acronym for my book, New Kind of Science, was something that people should be doing. And we tried to figure out what's the right institutional structure to do this stuff. We dealt with a bunch of universities. Can we do this here? Well, what department would it be in? Well, it isn't in a department. It's its own new kind of thing. That's why the book was called A New Kind of Science. It's kind of because that's an increasingly good description of what it is, so to speak. We were thinking about kind of the ruleological society, because we're realizing that it's kind of
love it.
It's very interesting. I mean, I've never really done something like this before, because there's this whole group of researchers who've been doing things that are really, in some cases, very elegant, very surviving, very solid. Here's this thing that happens in this very abstract system, but it's like, what is that part of? It doesn't have a home. And I think that's something I kind of fault myself for not having been more, when complexity was developing in the 80s, I didn't understand the danger of applications. That is, it's really cool that you can apply this to economics and you can apply it to evolutionary biology and this and that and the other. But what happens with applications is everything gets sucked into the applications. Mm-hmm. And the pure stuff, it's like the pure mathematics. There isn't any pure mathematics, so to speak. It's all just applications of mathematics. Mm-hmm. And I failed to kind of make sure that this kind of pure area was kind of maintained and developed. And I think now, one of the things I want to try to do, and it's a funny thing, because I'm used to, I've been a tech CEO for more than half my life now. So, this is what I know how to do. And, I can make stuff happen and get projects to happen, even as it turns out, basic science projects in that kind of setting, and how that translates into kind of, there are a lot of people working on, for example, our physics project sort of distributed through the academic world, and that's working just great. But the question is, can we have a sort of accelerator mechanism that makes use of kind of what we've learnt in sort of R&D innovation. And, but on the other hand, it's a funny thing, because, in a company, in the end, the thing is, it's a company, it makes products, it sells things to people. When you're doing basic research, one of the challenges is there isn't that same kind of sort of mechanism. And so it's how do you drive the thing in a kind of in a led kind of way, so that it really can make forward progress, rather than what can often happen in academic settings where it's like, well, there are all these flowers blooming, but it's not clear that
you have to have a central mission and a drive, just like you do with a company that's delivering a big overarching product. And that's
but the challenge is, when you have the economics of the world are such that, when you're delivering a product and people say, wow, that's useful, we'll buy it.
Mm-hmm.
And then that kind of feeds back and okay, then you can pay the people who build it to eat, so they can eat and so on. Mm-hmm. And with basic science, the payoff is very much less visible. Yeah. And with this physics project, as I say, the big surprise has been that, for example, the big surprise with the physics project is that it looks like it has near-term applications. And I was like, I'm guessing this is 200 years away. I was kind of using the analogy of Newton starting a satellite launch company, which would have been kind of wrong time. But it turns out that's not the case. But we can't guarantee that. And if you say we're signing up to do basic research, basic rheology, let's say, and we don't know the horizon. It's an unknown horizon. It's kind of like an undecidable kind of proposition of when is this proof going to end, so to speak? When is it going to be something that gets applied?
Well, I hope this becomes a vibrant new field of rheology. I love it. Like I told you many, many times, it's one of the most amazing ideas that has been brought to this world. So I hope you get a bunch of people to explore this world. Thank you once again for spending your really valuable time with me today.
Very fun stuff. Thank you.